Hello, we're now on section 1.5 of the summary questions. I've started the first ones. These are all basically on fireman diagrams. So, fireman diagrams, we have to remember that time is moving in this direction, okay? The angle that they come in at is not really representative of the angles they're actually coming in at. This is just a pictogram, a way of resembling it or representing it to us. The first question that we come across here is to sketch fireman diagrams for the electromagnetic force between two protons, a proton, electron and two electrons. So, as I say, the first one I started, okay, and what you see with the first one is that the protons come in, two protons, and they go out. No actual change of state happens here. This is just a force between the two protons, and the force carrier for the electromagnetic force is a virtual photon. So the two protons come in, a virtual photon is exchanged, and two protons go out. Okay, that's the electromagnetic force or the electrostatic force that's going on there. Now the next one confuses a lot of people. A proton and an electron. Okay, the reason it confuses a lot of people is people misrepresent that this means that the proton comes in and is deflected. We just draw it that way for convention. It's not actually showing its direction, just that an interaction has taken place. So what people want to do is do something like make the proton and electron come closer together, because they know that their charges are opposite and therefore it's an attraction, not a repulsion. They see this is a repulsion and an attraction should look different. So they're expecting something like this, but that's not how you write it. This is just a representation that a force has happened, and therefore it looks exactly the same as the one before. It doesn't matter to us that the way they interact is different, i.e. in this case it's an attraction, not a repulsion. All that matters is that a virtual photon has been exchanged. So C, well, just as easy. An electron in, virtual photon to another electron in, and then two electrons out. Very, very simple. If you get a diagram that you need to draw about electromagnetic force, be happy, easy marks. Okay, question 2. Question 2 asks us to sketch the diagram, the Fireman diagram, for beta plus decay and beta minus decay. So we've got to look at the two versions of beta decay. So beta plus decay first. Well, beta plus decay is going to happen when a proton turns into a neutron. Okay, which is beta plus is positron emitting. If we watched my video on section 1.4, you know that happens in a proton-rich nucleus, generally, where it's got too many protons. It wants to even it out, so one of the protons turns into a neutron. So we've got a proton in and a neutron out. Now a force carrier goes across here. Now we know that the decay of particles is nearly always representative of beta decay or some form of decay that we're used to seeing, and it will always exchange the weak nuclear force particle. Decay comes from the weak interaction, so the weak nuclear force particle, which will be a W. As to whether it's plus or minus, don't need to actually write that in yet, we can work that out as we go along. We know we're going to get a beta plus decay, so beta plus or E plus, because we know it's actually an electron. And one thing that we'll always remember is that if we're going to emit a beta particle, we're also going to emit a neutrino. When we come on to later sections, you'll see why that happens, what the conserving lepton number is the reason, and therefore that you'll see that this is a normal neutrino because this is an antiparticle. You'll always have a particle and antiparticle. Okay, so all you now have to consider is what type of boson we have here. Well, I always like to look at the charge and the way the charge is moving. So the proton has a plus charge, the neutron has no charge, the positron has a plus charge, the neutrino has no charge. Therefore the plus charge has gone from here to here. Therefore the plus is carried through by the W plus boson, which decays very quickly into these two parts. Part B, well, we're looking at electron emission or beta decay. So we're going to look at the same kind of examples last time. This time we're going to get the actual electron out, so beta minus. Because this is a normal particle, we'll need an anti-neutrino. Okay, we know the exchange particle is going to be the W, because it's W, it's the weak nuclear force, it's the W boson. And common sense tells us that if a proton to neutron gives us a beta plus, well, we'll be looking at a neutron to proton. Okay, and neutron to proton, we can now look at the charges. We have 0 on this side, 0 on this side, a minus there and a plus there. So the plus and minus cancel each other out on that side. The 0 and 0, that's fine on this. We've got the right particles coming in and out. All we've got to decide is, well, the charge, they're not cancel each other out. If we're going this way, to get a 0 to give out plus, we'll need to cancel it out by sending a negative in this direction. It's not a perfect rule, but this is how I try to work it if I can't remember off the top of my head. So we've got a 0 coming in. The charge has got to go somewhere. So here the charge came in. If it doesn't go out there, it must go out here. That's easy. Here no charge comes in, but we do get a charge out, so we must have the reverse charge here, so that added together they are 0. And that's question 2. Question 3 says to sketch a Fireman diagram for the interaction between a neutron and a neutrino. Okay, so neutron, neutrino. So we know our intake side because it's what the question's asked. So we're doing neutron, some sort of exchange particle, and a neutrino. Don't forget, try to put as much information as you can on these diagrams before you even have to think about it. We know something will come out here, and we can say it's very likely something will come out here. Now, we know this is beta decay just by another means. This time, a proton just randomly decayed into these objects here, or this object emitting these objects. This time, instead of random decay, what's happened is a neutrino has interacted with a neutron and kicked it off and caused it to happen. But the products will be the same, so we're looking at this neutrino to proton, because neutrino here, we're going to get beta decay is going to turn neutrons to protons. Neutrons to protons. So we've got a neutron coming in, we're going to have a proton coming out. Now, as you can see, before, when it was emission here, we had an anti-neutrino. The reason it's a normal neutrino is because it's now on the other side of the equation. When you look at the word way of writing this, I find that it actually is more obvious when we look at the rules, the conservation rules. But needless to say, at this point, if you're only up to section 1.5, the reason why that's now not an anti-neutrino will become evident later on. And we're going to get our beta particle out here, and we can look at the charges. 0 comes in here, plus goes out there, so what must, to even it out, and minus must go out there, and we can check it travels up there, everything is fine. So that is the interaction between a neutron and a neutrino. The next one is a proton and an anti-neutrino. Well, as you can imagine, this is going to be something similar, but the other way around. So we'll draw our fireman shape, our arrows. All this can be done without really having to think about it. Worst case scenario, it turns out they both come out up here and you screw the leg out. It's not too much to worry about. It tells us we've got an anti-neutrino and a proton. We know that this is going to be a weak interaction. We can tell by the things we've got here, which means we're going to have to swap between a proton and neutron. Now, when we went neutron to proton, we got beta minus. Quite obvious this time we ended up beta plus. And that also matches up here. We had normal particle, antiparticle, antiparticle. For charges, so plus coming in here, 0 going out there, so the plus must go this way, and check, yes, it goes up there. And there's our W plus. So that is the weak interaction caused by neutrinos. Question 3b, oh, that was part 1 and part 2, sorry. Part B, state the approximate range of the W boson and estimate its lifetime, given it cannot travel faster than the speed of light. Now, this takes a little bit of thinking about, but is actually, the maths is not too difficult. So, now the range of the W plus boson is given to us in the book, but it's quite easy to remember really. It's plus or minus really. It's a W boson. It's approximately 0.001 femtometers. Okay, so the range of that boson is very, very, very small. If you're not sure where it is in the book, page 14, very short range, no more than about 0.001 femtometers. So, it can't travel faster than the speed of light. Okay, so its velocity cannot exceed c. Okay, so its velocity must be less than c. But we know it travels very fast, so the best way to do this is to assume it can travel at c, or very, very approximately close to c. Okay, that gives us the maximum speed it can kind of travel at, which therefore gives us the maximum different range that it can go in a given time. We know that velocity is distance over time, so we can rearrange that to say that time equals distance over velocity. Okay, and we know the range because we've got that here, that's a distance. We know the velocity, well, we're going to estimate the velocity to be approximately c, to give us sort of the maximum velocity it could have. We've got d, we've got v, or in this case it will be c. We can calculate its lifetime, how long it can travel for. So, let's put some numbers in. T will be equal then to the distance, which is 0.001. Femto is times 10 to minus 15. And make sure you look that up and put that in correctly. and v, the velocity, well, we're going to take the speed of light to be its maximum, and that gives you an answer of 3.3 times 10 to the minus 27 seconds. Now you could say 3.3 is, considering we've taken a big leap of faith here about its speed, it's probably more accurate than is really necessary, but we can say it will be in the order or approximately equal to somewhere around 10 to the minus 27 seconds. So you could argue if we knew how fast it travelled, we could get an actual exact answer, but we can restfully estimate. It tells us that the speed of light is the maximum it can travel, or it can't travel faster than that. Therefore we can work on the speed of light, and then we'll put the numbers in and we get a rough idea of how long it survives for. Okay, question 4. It's a word question. It says state 3 differences between the W boson and the virtual photon. Now, the two easy ones, and one that people sort of get a little bit forget sometimes. The first one, let's make this up. So the W plus boson, or the W boson, has charge, hence we call it W plus or W minus. It has mass. In fact, it has a lot of mass, so much mass it has more than it should, and it's nicked some from nowhere. Brilliant aspect of quantum physics. And the last one that I would suggest is it undergoes different interactions. I.e., it feels different forces to the virtual photon. This is the force carrier for weak nuclear force, but the virtual photon, which has no charge, has no mass. So there's the two first ones. This one is electromagnetic, and this one is weak. And then part B, it says in both figures 4B and figure 5, so if I can get these in the camera, 4B, which is proton to neutron decay by the emission of a positron and a neutrino, and figure 5, which is the electron capture. Proton captures an electron, turns into a neutron and emits a neutrino. It says a proton changes in a neutron in both examples. Describe how these two processes differ. Okay, so the first one we've actually got up here. So it's this one. So this is a decay. So put my room, let's put it down here. So the first one, so proton to neutron in figure 4B is the decay of proton to neutron by emission of beta plus and neutrino. The proton to neutron in figure 5 Now I'll just draw that here because we haven't done figure 5, so it looks like this. Proton, electron, neutron, a neutrino, and it's also W plus. So you got plus comes in, 0 goes out, so it must go this way, and then the plus and the minus cancel each other out, so we get 0 on the other side. This is electron capture. So the electron has come in and been captured by the proton, and it turns itself into a neutron and emits a photon, neutrino. And that is the end of section 1.5. That's also the end of section 1.